So he looked specifically at the hydrogen atom. Okay? Each atom gives off a different spectra of light. And we know that when we go camping and we throw those fire packets into the fire pit and we see greens and we see blues and we see reds and brilliant oranges, sodium gives a color, copper gives a color, strontium gives a color, okay? Same as the fireworks. Those are all different metals. Potassium, not nitrate, but potassium, okay? And so he looked specifically at hydrogen. So he knew that if you put white light through a prism, it would be dispersed. So you'd go from white light in through a prism, and then you would get this really nice color of Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. So same idea here. He has a hot source emitting white light, goes through a diffraction grating, so either a slit, like the double slit experiment, or this is to show you that it's a prism. Okay, this has the slit in it. So either or, not both set up. It'll be either or. And then out the other side comes a spectrum of different colors or different bands. Okay. So he put white light from a glowing source through an unexcited gas, meaning that it doesn't have very much energy, and then through the prism. And so what he saw was that there was this spectrum, and it had dark lines and it had bright lines. Dark lines were in relation to photons that had very specific frequencies, wavelengths, energies, take your pick, that were missing from the spectrum. And so when we look back to it, when we look back to Planck, where we learned about Planck's constant, we know that energy, wavelength, and frequency are all related here. Okay, so whether it's frequency, if I increase the frequency, my energy will increase. If I increase the wavelength, my energy will decrease. Okay. If I increase my energy, my wavelength will decrease. If I increase my energy, my frequency will increase. So it looks at those three pieces for the relationship. When we take this bright energy and we put it through a cold gas, something that it's not inert, so it's not an argon or a helium or a neon, but it's a cooled gas so that it slows down the molecules moving, because we know as we heat up molecules, they move more quickly. When you move more quickly, you have more energy. Okay. Then it went through either a slit or a prism. He particularly chose a prism. We get this dark line spectrum and right here. So here's dark line, here's dark line, dark line, dark line. Okay? And we kind of touched on that in EMR, where we looked at N being the number of those dark lines apart or bright lines. We didn't discriminate between dark lines and bright lines. Here we're focusing specifically on dark lines. Okay? What he said was that an unexcited gas must only be able to absorb certain photons and not the entire spectrum. If it could absorb the entire spectrum, we wouldn't have these dark bands. We wouldn't have these gaps in the spectrum. Okay? And so Planck, if you remember, that's where we fit in, or we flipped over into photons as packets of energy away from the wave theory and into the particle theory. This supported it. Bohr was able to support Planck's theory. Once he did that piece, he then took the experiment and he passed light from an excited gas, so one that's been energized, so chances are it's been heated up or It's had energy, electrical energy supplied to it. So like that CRT tube that I showed you, okay, through a prism or a grating. And then what he observed was that there was no continuous spectrum produced, but only thin bands that had colors. So kind of the flip. Okay, so before we took an intense amount of energy, pushed it through a cooled gas, ran it through a prism, and we saw these gaps in the continuous spectrum. Now he's taking the light and he's putting it through hot gas or energized gas. Then he's running it through a prism and he's like, okay, I don't see any color, but now I'm starting to see these bright bands. So cool gas was dark bands, hot gas, he's starting to see these bright bands. And where we saw color with the cool gas, we see blank dark spaces. And we call this bright line spectrum or line emission spectrum. And so then he was able to say that the excited gas must only be able to emit certain photons, okay? Just like cooled gas can only absorb. So it's taking on, if it's a cooled gas, it's taking on the energy. And if it's a hot gas, it's releasing that energy. Okay? And what we see, if we take these two spectra, so hydrogen absorption spectra and hydrogen emission spectra, we see that where we have the dark bands in the absorption spectra matches up with the bright bands in the emission spectra. And this is how we test chemicals in the industry. So, yeah, absorption is with cold gas and emission is with hot gas. So the cool gas, what it's doing is it's taking the energy from the light, the quote unquote white light, and it's taking that energy, and then whatever's left is going through the prism, and that's where you get those dark bands. That's what's being absorbed. Okay? Okay. And so then every element has its own atomic spectra. And so then he came up with these three proposals. He said, for the electron to occupy any one of the allowed energy orbits, it must possess the energy allowed for that orbit. It can't be found, electrons cannot be found in between orbits. This is what Bohr has said. When an atom absorbs a photon, the electron in the atom will move up into a higher energy orbit. And when the atom emits a photon, it will move down into a lower energy orbit. So this is, well, I'll show you, draw you a picture. So let's look at, okay. If we take this photon, and this photon is absorbed, what happens is, here's an electron sitting right here. Oh, I've got one too many circles. That's okay. Okay? If we absorb this energy, what happens is I'll draw the third one, but it doesn't matter. Is this electron will be now found in the next orbit. So here, the electron is in the first orbit. Now we find it in the second orbit. Okay? So if you absorb a photon, it will move up an orbit. So so you know how when we talk like calcium, I don't even know if I have a data book right here. Anybody have a right here? Anybody have a periodic table handy? Calcium has how many protons? No, that's the charge. Has how many protons? That's the atomic number. This one's being sent out. This is a photon emitted. What we see is, here's the nucleus, is we now see that electron go from this layer here into this layer here. Okay, so it's going from the second orbit in this particular diagram into the first orbit. And where we see that, we have emission. And you have bright band. Bright line spectrum. Okay? So it moves down in energy level. And that makes sense. This whole idea, here's a blank, where's the blank? If we looked at here, and we know we talked about calcium, there's 20 protons here, 2, 3, there's 4 energy levels, right? There's 2 sitting out here for calcium. And what's easier? What do we always say? It's easier to get rid of 2 electrons than it is to take on 6 electrons, right? So what they want to do is they would want to pump in enough energy that we kick these guys out. And so if this is calcium, maybe what we have over here is sulfur, and it's a 2 minus, and it will take on, because it's got 6, right? 1, 2, 3, 4, 5, 6. It will take on these ejected electrons here and complete their shell. So all those things that we learned in Chem 20 are going to come here. When we absorb and we kick it into another level, or we emit and we kick it down a level, we change the energy levels. Okay? This is what it looks like. So he has energy level diagrams that helped explain this. So, whoops. And yes, they're unequally spaced. So here is n equals 1, n equals 2, n equals 3, n equals infinity. Okay, this is the outermost level. So we've been talking about those broadband, those dark bands and those bright bands when we were in EMR. That's what these are. These are energy levels. Okay, they're energy levels for the electrons to occupy. Up here, we have ionization, and down here we have what's called the ground state. Okay? So what happens is we have to have, in ionization, the electron has to have gained enough energy to leave the atom. Okay, this is those 2 electrons that we want to leave calcium, And sulfur has 2 electrons that it wants to take on. Ground state is the level closest to the atom. Oops. If the atom is unexcited. This is no energy being applied to this atom. It's just existing. Okay? There's standard values that exist. Here, this is negative 13.6 EV. What does EV stand for? Electron volts. We've seen this before. Negative 3.4 electron volts, negative 1.5 electron volts. And when it's completely ejected, is 0 electron volts. Okay? How are what related? Like here, this one here requires no energy or next to no energy to exist. These ones here, as we go up, requires more and more to be excited. So see, we're going from negative 13.6 and we're getting closer to the positive side. So it's requiring more and more energy. Energy is not, well, it is electron volts. If you take a joule and you multiply it by the 1.6 times 10 to the negative 19 joules per electron volt. Okay? So we can look at the relationship in energy. So change in energy is equal to final minus initial. Okay? This particular change in energy is the energy of a photon. We're not looking at wave theory, we're looking at particle theory. How do we find energy of a photon? Hc over lambda or HF. So now we're taking some EMR knowledge and we're bringing it forward into the atomic physics unit, the nuclear physics. Okay? Here's the kicker. If delta E is negative, what do we know? Oh, you guys won't know this. You won't have Chem 30 yet. That's okay. Energy is released, which we're going to learn is exothermic, means releasing heat, releasing energy. This photon is emitted. If the delta E is positive, energy is absorbed, and your photon is absorbed. Okay? And if we have a positive energy, it requires energy, which means that it's endothermic. We've seen those words. We haven't delved into those words. Okay? And it stands true. If I have it passing through a cloud of cold gas, it's not hot. There's not a whole lot of movement in the ions, and so the energy would be required. It's absorbed. If I have a photon that's emitted, there's high energy. In order to have high energy, you need those particles to be moving rapidly, right? The things that we learn in Chem 20. Energy is released. Okay. These values here are common. The 0, 1.5, 3.4, 13.6, they're common, but they're not standard. if we looked at this example, it says use the following information to answer the next 5 questions. So this is kind of a typical diploma setup. They'll give you something in a box and it'll tell you it's the next 2 questions, it's the next 3 questions. We don't have written answers on the diploma like you do in math. We have multiple choice and numerical response. Okay. The energies of an electron within an atom are most often given relative to ionization as shown below. So R level n equals 1, n equals 2, n equals 3, n equals 4, n equals affinity, n equals 1. Okay, shows us that we start at 0 electron volts at ionization and we're at negative 14 electron volts at ground state. So ground state is closest to being a dormant atom. So it says determine the energy of a photon absorbed released as an electron makes a transition from D down to B. Okay, so we're going to look at change in energy from initial is ED and final is EB. So EB minus ED, because we start at D and we end up at B. So negative 10 electron volts minus negative 2 delta E has what value? Negative 8.0 electron volts. Okay. Now, the negative sign tells us it's emitted or absorbed. It's emitted. Okay? If it's emitted, that means that our energy is released because I ended up with a negative value. Okay? It says determine the number of photons of different wavelengths that could possibly be produced due to an electron at level C moving to ground state. So here's level C. If we have an electron sitting at level C, we can move down to level B. We can move down from C all the way down to A, or we can move from B down to A. So there's 3 different ways go from C directly to A, C to B. Once it's at B, it can still go down to A. So 1, 2, 3. Okay. Third question says, determine the frequency of the photon absorbed or released when the electron in the atom moves from C all the way down to A. Okay, and is the photon absorbed or released? So we know that to determine frequency, the energy of a photon is equal to Planck's constant times frequency. That's how we're going to solve this, because this is what we're looking for right here. What piece of information don't we have? We don't have the energy of a photon. How do we get the energy of a photon? Delta E is equal to EF minus EI. EF being E at the A level and EI being E at the C level. So negative 14 electron volts minus negative 7 electron volts. So the change in energy is, okay, at this point, can we tell if this photon has been emitted or released? Yes. How, Avery? Because it's a negative. Okay, so we can answer that part of the question. We still have to figure out the frequency. So frequency is going to be equal to the energy over Planck's constant. Planck's constant comes to us in two values, electron volts and joules. Because our energy is negative 7.0 electron volts, we want Planck's constant that's also in electron volts, which is okay. And so we get what for a value? Yep. A unit for frequency is hertz. When we go back to significant digits, 2, so 1.7 times 10 to the 15 hertz is our energy. Now, what I've done is I've dropped that negative sign. That negative sign simply tells us emitted, or absorbed. It has no bearing on the value of frequency, wavelength, or energy. It's an indicator. Just like in Physics 20, it told us left or right, north or south, east or west, forwards or backwards. It's a direction. Same thing here. It tells us emitted or absorbed. Okay? Okay. 4 says, I'm going to leave this here in case we need the diagram. 4 says, determine the wavelength of a photon required to ionize an electron that was initially at ground state. So we want to go from here. We want to go from, I'm going to pick a different color. From here all the way up to there. This is question number 4. Okay, that's what we want to do. So change in energy. Well, actually, it's asking us to find the wavelength. How do we find that? Hc over lambda. H is Planck's constant. C is the speed of light. Wavelength is what we're looking for. Energy is what we don't have. So energy is going to be found from E final minus initial. It's going from the ground level up to ionization. So our final is ionization and our initial is ground state. Ionization is what value? 0. And ground state was negative 14.0 electron volts. So delta E is positive 14.0 electron volts. Was this emitted or absorbed? Absorbed. Okay, so we can answer that piece. Now we look at our photon. Wavelength is going to be equal to hc over energy. Again, make sure that you're using the electron volts because our numbers are in electron volts. 4.14 times 10 to the negative 15 electron volt seconds. 3.0 times 10 to the 8 meters per second divided by 14.0 electron volts. And our wavelength is 10 to the which, Daniel? Negative 8 meters, right? Seconds cancel out, electron volts cancel out, we're left with meters. Okay. Any questions so far? We're going pretty rapidly through this. No? Okay. Last one. An electron at ground state, so this is ground state down here, is struck by a passing electron having an energy of 9 electron volt, and the atom's electron absorbs, that's some keyword there, absorbs as much of the energy as possible. Determine the kinetic energy of the passing electron after it collides with the electron in the atom. Okay, so kinetic energy is going to come from what? Well, we need to go all the way back to this. Energy in equals energy out. So kinetic energy here is going to be equal to the total kinetic energy is equal to EK final minus EK initial. This is total. Change in kinetic energy. But it's asking us to find the kinetic energy of the passing electron. That's this guy here. So in order to find EKI, we're going to go EKF minus the change in energy. This change in energy happened to be the energy that was absorbed. Okay? When the energy is absorbed, we know that it can move only up an energy level. Okay? And it has to have something that is a gain of, or a gain in energy of 9.0 electron volts or less. Because anything more than that would push it into emitting. So how do we find this delta E? Because that's a piece we don't know right now. Delta E is going to be equal to E final minus E initial. So when we look here, it can't be, it says 9 or less. So it can't be level A, and it can't be level B. The best we can do is level C. Pardon me? Can't see? It's right there. No. Okay. So we're going to start at, we're going to end up here because we're going from it says here, another piece of information here, is it starts at the ground state. So ground state is negative 14.0 electron volts. And 9 electron volts or less, the best we can do on this chart that was provided to us is 7. So we end up with negative 7 minus negative 14, positive 7 electron volts. This positive sign supports that it's absorbed, which is what it says here. It says the atom's electron absorbs. Okay. All right. So then it asks for initial kinetic energy. No. Yes. So our final electron energy here is 9 electron volts. The initial electron, or the absorbed energy here is what we calculated, 7 electron volts. So it started out with 2 electron volts.